Properties of metals. Typical physical properties of metals: high melting points, good conductors of electricity, good conductors of heat, high density, malleable and ductile. Some metals have properties that are not typical. For example, mercury has low melting point as it exists as a liquid at room temperature. Elements in group 1, very low melting points, very low densities. For example, sodium is less dense than water and so it floats. Physical properties of some metals in details. High density. The reason: atoms are usually packed together as closely as possible. Most metals have high density because there is little empty space between the closely packed atoms. As given in the diagram, 3D arrangement of atoms in a typical metal and simplified diagram of a metal structure. The atoms are packed together very closely. The reason for high melting point and boiling point: as metals are giant lattice structures, the number of electrostatic forces to be broken is extremely large, and so metals have high melting and boiling points. These are more similar to those for ionic compounds than for covalent compounds. The reason for malleability and ductility: malleable substances can be bent or hammered into shape without shattering, while brittle substances shatter when bent or hit. Metals are described as ductile because they can be drawn out into thin wires. The structure of metals consists of layers of metal ions. These layers can slide over each other when a force is applied. This means that the layers of the metal can be hammered flat and that they can also slide over each other to make thin wires. Metallic bonding allows the metal to change shape without shattering. Physical properties of metals. The layers of atoms can slide over one another as shown in the figure. Conduction of electricity. Substances conduct electricity because they contain charged particles that are able to move. When a voltage is applied to a metal, the delocalized electrons travel through the lattice structure. The movement of these charged particles forms an electric current. Notice that the metal ions in the metallic lattice are held in fixed positions and are not able to move. What are alloys? Alloys are mixtures of metals where the metals are mixed together physically but are not chemically combined. They can also be made from metals mixed with nonmetals such as carbon. What are the properties of alloys? Alloys often have properties that can be very different to the metals they contain. For example, they can have greater strength, hardness, or resistance to corrosion or extreme temperatures. Alloys contain atoms of different sizes, which distorts the regular arrangement of atoms. This makes it more difficult for the layers to slide over each other, so they are usually much harder than the pure metal. Brass is a common example of an alloy which contains 70% copper and 30% zinc. Bronze is also another example which contains copper and tin. So this is the figure showing alloy, the arrangement of alloy, element X and element Y, that makes it difficult to slide over one another. Another example is stainless steel, which is an alloy of iron, 80%, chromium, nickel and carbon also present in stainless steel. It's strong and hard with a very high resistance to corrosion because of chromium. It is used for cookware, cutlery and industrial chemical plant. And now we are going to determine the reactivity series using some experimental evidences. This is the reactivity series: potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, gold. Least reactive is at the bottom and most reactive at the top. So experimental evidences. First evidence: reaction of metals with cold water. The above metals such as potassium, sodium, calcium and all, they reacts. Potassium reacts violently, explodes with cold water. Enough heat is produced to ignite the hydrogen gas produced, and the hydrogen gas burns in air. The reaction is given Metal plus water gives metal hydroxide and hydrogen. Similar is applicable to all the metals below it. Sodium reacts violently, calcium reacts readily, magnesium reacts very slowly with cold water. Zinc, iron, lead, copper, silver, no reaction occurs. That indicates that reactivity of metals increases up the series. The next reaction is reaction of metals with steam. With steam, they produce oxides and hydrogen. For example, magnesium reacts violently with steam. Magnesium oxide, a white powder, and hydrogen produced, bright white glow produced during the reaction. These are the observations. Zinc, yellow when hot and white when cold, zinc oxide. Iron reacts slowly with steam. Iron tetroxide and hydrogen is produced. Reaction is easily reversible, so iron need to be heated constantly for reaction to take place. Lead, copper, silver, no reaction with steam. No reaction with cold water, no reaction with steam. So this indicates that again the reactivity of metals increase up the series. This is how the setup of the apparatus to do the reaction of metal with steam. Magnesium ribbon is heated, bright white glow is produced, and hydrogen gas is being tested with a lighted splint. So the lighted splint goes off with a pop sound, indicates that the gas present is hydrogen. Reaction of metal with steam. Hydrogen gas collection is shown here. You can collect the gas. The next evidence is from the reaction of metals with dilute hydrochloric acid. Potassium sodium explosive reaction. So we should not carry out this reaction in the school lab. And the product obtained by reacting of a metal with hydrochloric acid is metal chlorides and hydrogen gas. Potassium gives you potassium chloride and hydrogen. Sodium gives you sodium chloride and hydrogen. Calcium reacts violently. Magnesium reacts rapidly. Zinc reacts moderately fast. Iron reacts very slowly. Lead, copper, silver, no reaction occurs, which is again giving a hint that reactivity of metals increases up the series. This is how we set up the apparatus for testing the metal with acid. Metal X, metal Y, metal Z, taking in the same amount of dilute hydrochloric acid. The reactivity of metals is based on the amount of bubbles produced and how fast the reaction occurs. The next one is reduction of metal oxides with carbon. This reaction is used to compare the reactivity of metals. The more reactive a metal, the more difficult it is to split up its oxides. As we know, potassium, sodium, calcium is more reactive. Magnesium is more reactive. So when you treat the magnesium oxide with carbon, no reaction because magnesium is highly reactive. Whereas when you treat copper oxide with carbon, copper oxide is reduced to copper by the reducing agent carbon. That indicates that it's easy to split copper oxide than magnesium oxide. Because magnesium is being more reactive metal than copper in the reactivity series, its oxides do not decompose when heated. And the gas produced is carbon dioxide, which can be tested using a lime water test. This reaction again gives the idea that highly up in the reactivity series are more reactive metals than below. So this reaction, metal oxides with carbon, we can make use of this in different fields. Metals can be extracted from their ores by reduction with carbon. That includes metal from zinc to silver. The metals above zinc in the reactivity series cannot be reduced by carbon. These are very stable. They can be only separated by electrolysis. So these are the two things, reduction and electrolysis. Reduction happens for the metals from zinc to silver. Above zinc, only can be separated using electrolysis. This is how we reduce mixture of metal oxides and carbon. This is an apparatus setup. The next reaction is reduction of metal oxides with hydrogen. So here hydrogen acts as a reducing agent. Hydrogen reduces metal oxides to its metal. Example is shown here. Iron oxide plus hydrogen gives iron plus water. Metals above iron in the reactivity series are not reduced by hydrogen. Only below iron in the series can be reduced by hydrogen. This is how the apparatus is. Hydrogen gas is passed through metal oxides and undergoes heating so that hydrogen can reduce the metal oxides to metal. The next reaction is displacement reaction. A more reactive metal can displace a less reactive metal from its compound. That's called a displacement reaction. For example, magnesium is reacting with copper sulfate. Magnesium is highly reactive than copper, so magnesium can displace copper from its compound copper sulfate, which produces magnesium sulfate and copper. This is a basic example of a displacement reaction. Reaction of metal with metal oxides. This is clearly a very vigorous reaction as magnesium takes oxygen from copper. The equation is shown here. Unfortunately, this reaction is so violent that it is impossible to see easily that any copper metal has been formed. In fact, because of the temperatures created, any copper that is formed is going to react with oxygen in the air to go back to copper to oxide again. But the vigor of reaction shows that magnesium is definitely higher than copper in the reactivity series. The reaction between aluminum and iron 3 oxide. This competition between aluminum and iron again shows that aluminum is more reactive metal than iron, and it takes the oxygen from iron 3 oxide to leave metallic iron. As you can see in the reaction, aluminum plus iron 3 oxide gives iron plus aluminum oxide. This is a question for you. Will silver react with aluminum oxide? No, because silver is less reactive than aluminum. Aluminum is a long way above silver in the reactivity series, and so the silver is not strong enough to take the oxygen from it. Will copper react with hydrogen oxide? No, copper is below hydrogen in the reactivity series, and so copper is not strong enough to take the oxygen from it. One more reaction we can see here. Metal atoms react with non-metallic elements or compounds to form metal ions. Metal atom is losing electron to form metal ion, which is called oxidation. This reactivity also depends on the ease with which it forms metal ions. A metal higher up in the reactivity series has a higher tendency to form its positive ions. So in that way also we can arrange the metals in the reactivity series. More readily forming positive ions will be more reactive metals that will be at the top of the reactivity series than which is at the bottom. The final reaction is action of heat on metal carbonates. Some compounds are more stable than others, so if they are stable, they are very difficult to decompose them by heat. That's called thermal stability. Thermal stability can be tested by heating them in a dry test tube. The more reactive a metal, the more difficult it is to decompose its compound, the more thermally stable it is. Potassium carbonate and sodium carbonate are showing stability towards heat. Carbonates of metals below sodium in the reactivity series decompose to oxides of the metal and carbon dioxide. Metal carbonates decomposes to form metal oxides plus carbon dioxide on heating. Summary of that: potassium carbonate, sodium carbonate, no effect on heating. They are thermally stable. Calcium carbonate, magnesium carbonate, zinc carbonate, lead carbonate, iron 2 carbonate, copper carbonate decomposes on heating to give carbon dioxide gas and the metal oxide. Silver carbonate decomposes to give silver oxide and carbon dioxide, but silver oxide produced is thermally unstable, so it further decomposes to form silver and oxygen. This shows that decomposing thermal stability decreases down the reactivity series. Higher up in the reactivity series, the metal carbonates are more stable towards heat. This is an apparatus for testing metal carbonate decomposition, and the gas produced is carbon dioxide, as we know, can be tested using lime water test.